Hey guys, this is second part of the Deterministic Finite Automata or DFAs. Let's see what we got for this session. So in the previous lectures, what we learned, we started constructing machines. What was the purpose? It was the simplest machine that could understand formal languages. And just remember that both formal language and these machines are mathematical models. What we learned in the previous lecture, we talked about the building blocks and we talked about how it works. So our knowledge so far is enough to see how the DFAs work in action. All right. So in this lecture, we try to analyze the behavior of some DFAs and we put some strings in the input and trace the machine's behavior. And after that, we start designing some machines for some formal languages. Okay, we will follow the templates that we already talked about. So you remember we have 8 steps, and up to this point in the first lecture, we talked about these 4 things. So the other things that we owe you is when the machine halts and how it accept or reject the strings. And also we would need to know about the automata in action, how it behaves in action, and we leave the rest of that for the other lecture. Let's start with DFAs in action. Intentionally, I put a on-off switch here. This is the first one that we want to analyze, so I try to go step by step to make sure that we are all on the same page. When I turn this switch to on, my question is what would happen? We learned before that what will be the starting configuration. The goal is to input ABB into this machine and trace it. Just to review what we learned before, what is the output for the starting? We learned that the output start from reject. Okay, how about the clock? The clock starts with the 0. How about the control unit or the transition graph? This guy, the Q0 or initial state, will be activated. And how about the tape? The string will be written on the tape and the cursor or the read head will point to the leftmost character or symbol. So this is the starting configuration as we talked before. Okay, let's see. This is the starting point. From now on, what would happen? On the first time frame, the first symbol will be read and it will be sent to transition graph. Transition graph, based on the logic for transition, will decide that it should go to this way or this way. It depends on the input, right? And what is the input? It is A. So based on this design, the machine moves to Q1. And then what would happen? The head will move to the right, one symbol to the right. So this is what would happen in the next slide. Okay, so now we are here. And as we said, we are on time frame 1 and the tape and head is pointing to this B. Okay, the same thing happens. This guy will be read and sent to the transition graph. Transition graph make a decision this way or this way. Since it is B, based on this design, it goes this way. And the clock will go here. And this head will move to the right. Okay? And now what? The same thing. Yeah? This go here and it goes here. And the head will point to this empty cell, right? And we know that when the head or the cursor point to the empty cell, the machine stops, right? So in the next slide, the machine stops here, which is an accepting state. Then, because the head is pointing to the empty cell, the machine stops in an accepting state. And that's why we say that based on this design, the machine accept this string. So this output will change to accept. Okay. So in other words, in summary, we can say that this design or this transition graph accept A, B string. All right. Based on this knowledge that we just got from the analyzing this machine, now we know that how the machine stops. So before going further, let's discuss about when DFAs halt or stop. Okay, based on our knowledge so far, we noticed that DFAs halt if and only if all input symbols are consumed. And how can we show this statement with a logical statement? Since we have if and only if from the discrete mathematics, we know that if and only if is equivalent to a biconditional logical statement. So because of this, when we say DFAs halt if and only if all input symbols are consumed, we can represent these two statements, DFAs halt, all, all input symbols are consumed, with this biconditional logical statement. So something like this. And now let's symbolize whatever we said so far. DFA's halt. In this course, I will show it with H, and all input symbols are consumed. I always show it with C, which is from consume. And this H is coming from the halt. This logical statement will be something like this. Let's input another string, A, B, B, A, and let's see what would happen. Okay, I think we have enough knowledge to understand that this A, it goes here, this B, it goes here, and this B, it goes here, and this time we have another A here, so it goes here. Because this guy is saying that if either it is A or B, move to here. Okay, let's see what would happen. Okay, so what was the difference here? This time machine stopped because this is pointing to the empty cell, but it stops in a regular state. And that's why we say that the machine did not understand ABBA, and this output is not changed. So the machine rejected this string. Okay, another example. This time we have BA. Okay, BA The B goes here, and this time the machine moves to Q4, and then it will read A. And since Q4 does not have any other outgoing transition except this guy, so this loop keeps the machine in Q4. So after reading the A, machine loops here and stops here. So it means that machine stops in Q4 again. What is the conclusion here? Machine rejected the BA. So BA was not understood. Okay. Another example. Oh, this one is very interesting. This time we want to feed or input lambda here, which is an empty string. Let's see what would happen in the starting configuration. This is the input tape. What should we put here? Should we put lambda here or we should leave it blank? Yeah, we should leave it blank because lambda is not a symbol for showing the empty string. It's just a concept, right? So empty string, it means that an empty cell. So the configuration will be nothing writing on the input tape. The tape, the head or cursor will point to the leftmost, which is still empty, and this guy will be activated, this guy will be activated, and the output showed reject. When we start the machine, then what would happen? Immediately, the cursor is pointing to the empty cell. So based on our knowledge so far, when the cursor is pointing to an empty cell, machine stops. So we predict that when we turn on the machine immediately stops. It stops where? It stops here, which is regular states. So we predict that this machine does not accept lambda. Let's see. Now the question is when machine accept or reject a string. Here is the logical representation of accepting. First, we focus on accepting. DFAs accept a string W. We represent it with A, which is the first character of accept. If and only if three conditions needed to be satisfied. First of all, the machine should halt. When machine is running, it does not accept anything. So first condition is when machine halts. All symbols of the W should be consumed. When we have a tape and when we have a string written on this, until we finish the last characters, and when the cursor does not point to the empty cell, the machine does not stop. So this is another condition for accepting the string. What else we need? The machine should stop in an final state or accepting state. So this is the third condition. If we summarize all of these three, let's see what we get. So as you see, we have these three conditions that should be satisfied, and there is an and between them. So all of them should be satisfied. So machine should halt, all of the symbols should be consumed, and machine should be in the final state. In that case, we would say, hey, a string was accepted. But let me remind you about one point here. We just said in the previous slide that halting and consuming have the same value. If you remember, we said machine halts if all of the characters are consumed, and vice versa. If all of the characters are consumed, then machine halts. So it means that H and C have the same value. And from the logic, you remember that when we say P and P, it is always equivalent to P. So instead of having two of them, we can eliminate one of them. So H and C has the same values. We can remove one of them. Let's say, for example, H. So in this case, we can summarize or simplify the accepting logical statement like this. When a string will be accepted, we have now two conditions. All of the symbols are consumed and machine stops in an final state. Now the question is when machine reject a string. Okay, so since we understood and formulate the accepting condition, we can play mathematically with that statement and produce the rejection. What does it mean? Yeah, let me just remind you, we have two logical statements. P by conditional Q is equivalent negation of P by conditional negation of Q. So it means that we may negate both sides of this and we still have the same logical statement. It means that these guys are equivalent. What is this one? This one is the De Morgan law. De Morgan law, it says that if you distribute the negation inside this parenthesis, all of these elements will get a negation. This guy will change. The and will change to or, and if we have or here, it will change to and. Okay, so based on this two relationship or property, now we can play with our logical equivalency here and we can apply first of all this guy. So we negate both sides of this and we get this guy. And then we use the De Morgan's law and we distribute this negate inside this parenthesis and we will get this. So this is the rejection logical statement. Why I am saying this? Because this was accepting, negation of accepting will be rejection, right? So this will be the rejection. Okay, now let's translate that when a string will be rejected. What is the plain English explanation or translation of this? This is saying that DFA rejects a string, this guy, if and only if at least one symbol of W should be not consumed, right? So this is the negation of all symbols should be consumed. The negation of that will be at least one symbol is not consumed, or the machine does not stop or halt in a final state. So it should be in a regular state. This is the flow chart of how the machine works. This symbol or this icon shows that this is just for your information. Yeah, you can go over this flow chart and see how it works. In the next slide, we have the pseudocode that all of these explanation that I gave you, we have this pseudocode here. Okay. Now let's analyze some machines to get more knowledge how they work. So here is an example. The question is, what language this machine will accept? So we need to analyze that which strings goes and reaches here because we just have one final state. Therefore, we need to understand and know that when machine stops here. Okay, when we analyze this, we see that if the string is A, it goes here. If it is B, it goes here. If it is B, it goes here. So definitely one string that will be accepted is A, B, B. Okay. Anything else, can you imagine that you put in the initial state here and it reaches here except the ABB? Can you imagine any other string? Yeah, you can pause the video and think about this. After some thinking, probably you will say, no, that's the only string that will be accepted. So in this case, we would say, hey, the language that this machine accept is this simple language, A, B, B. So this was very easy. Let's make it a little bit more complicated. How about this one? Oh, this one is the same machine. We just change this guy and this guy as the final state. So if machine stops here, the string will be accepted. If machine stops here, the string will be accepted. And this guy, we already know that. All right. Okay, so let's put together all of them. So which string will stops here? Lambda. Yeah. Which string will stop here? Only A. And we already know that. What would happen for these states? That was already A, B, B. So these are the only strings that if we input in this machine will accept that. Otherwise, all of the other strings will be rejected. Now, let me give you some notes about how the machine works. We don't need to show the output and the clock any longer. All right. Second note is the role of Q4. The Q4 has a special role here, and it's important to know that. So the Q4 is in fact a trap. What does it mean, it's a trap? When a machine moves to Q4, it can never go out. So it will stuck here. So why should we use this? When we want to reject some strings, we send the flow of the processing to this trap. For example, for this machine that only accept A, B, B, right? We already know that. In other words, if a string starts with B, for example, BAA, something like this, it goes instead of this way, it goes this way, and it goes to the trap and will stuck here. So after the B, anything else, this guy will loop here because either A or B will keep the machines on the Q4. So that's why it stocks here, right? If a string, let's say, start with A, so machine goes from here to here. Now after that, instead of B, let's say it has another A. Again, machine goes this way. AA goes this way, and AA will be rejected. AA, let's say B will be rejected. AA, B will be rejected, and so forth. anything with AA will be rejected. Okay, so I think we have enough examples so far to understand that this is a trap. So during the design, I will show you how we can create a trap. So the trap sometimes is called black hole, sometimes I call it hell, for example. Yeah. And we use, as I said, the trap to reject majority strings of L bar. Why majority? Why I didn't say all of them? Because, some other states like this one, reject the strings. It's not the case that only trap will reject all of the strings. Let me take another example. The question is what language this machine will accept. Yeah, let's start from the Q0. As you see here, we have a loop here that it has A. So it means that if I put any number of A's, machine loops here and stop here, right? So any number of A's goes stop here, and when the machine reaches the first B, it goes this way, right? And goes here. All right. So any number of A's followed by a B goes here, right? And after that, if the string has more things, it goes here and it will be stuck here. So this guy, in fact, is our trap. Okay, so let's summarize one more time what language will be accepted by this machine. We learned that any number of A's will loop here, and when we have and B, machine goes this way and will stop here if that's the only thing that we have, right? So any number of A follow by a B. So this is explanation of what language will be accepted by this machine. Now the example asks us that we need to represent this language by a set builder. It will be very easy for us. Any number of A's, it will be A to the N, followed by B, it's just the B. Such that, okay, so A and B are constant. The only thing that needed to be explained after the colon is n. What is n? Any number of A. It can be 0 or more, right? So n greater than or equal to 0. So this is the language that will be accepted by this machine. Now we'll need to use all of our knowledge to design machines, which is the most exciting part of this course, designing machines. And it definitely would need some practice. Okay, so let's start with the first language. The first language is easy, so a to the n greater than or equal to 0, and it is over this alphabet, A, comma, B. Design a DFA to accept L. Sometimes it helps us to enumerate the language and know that what kind of strings should be accepted. So we enumerate this language, A to the N, it means that any number of A's, and it starts from 0. So if n is equal to 0, it will be lambda. If n equal to 1, it will be a. And yeah, we understand that it will be a, and so forth. And you know that we can represent this with a square and a cube, a to the 4, and so forth. Okay, that's the easy one. We start from the initial state. And since the lambda should be accepted, we need to make the initial state as accepting state. And what else? Any number of a's should be accepted too. So can I put a loop here and say, okay, if you see any number of a's, stay here in the initial state and it will be accepted. So any number of a's, do you agree that, for example, if we have one a, it loops and stop here. If we have a, it it will loop twice and stop here again, right? So you agree that all of the a's, including lambda, will be accepted here. Machine stops here. Okay, so since the alphabet is AB, it means that we may have some strings that it contains B, right? Then what? We need to create a trap for that. So if machine sees any B, we need to send it to a trap here, right? And how can we create the trap? You just create a loop here, and if it is A or B, just loop here and stops here. So this will be our trap. All right. Okay. So just for testing, let's make some tests here. We know that all of the lambda A and AAA, so all of these string from L will be accepted here. We have no problem with that. How about the L bar? The L bar is anything except this L, right? For example, something like, let's say BA, for example, or BB, or I don't know, AB, for example, and so forth. Yeah, anything except lambda A, and so forth. Okay, so let's have a test here. BA, B goes here and stops here, so will be rejected. BB, B goes here and another loop here, so BB will be rejected and so forth, right? Let's try another one, AB. So A will loop here and B goes here and stops here. So as you see, the machine will reject all of the L bar. So this is our design, all right? But this example has another question. What would be the design if n is greater than or equal to 1? So instead of this guy, if we change it to 1, then what would happen? Okay, so let's enumerate what was the difference. It starts from 1, it means that we eliminated the lambda. So it starts from 1, it will be a square, a cube, and so forth, right? So that's the same language except the lambda is eliminated. All right, so how can we do that? So it means that at least we need one A. Okay, no problem. At least we need one A, right? So we move it to here, and now we make this guy as an accepting state, and we put a loop here, A. So this way we moved from the initial state because lambda should not be accepted, right? At least we need one A. Just we use this A to move to this state. So any number of A's will loop here and it starts from 1A, right? Okay, we still need a trap. Yeah, the same way. If we have a B here, we create a trap here. How about if the machine starts with B? Ah, that's another good question. So it means that we need something from here. Yeah, no problem. We send it to trap this way. Okay. As a general rule, let me give you a hint that how you should design your machine that you don't miss anything. Okay, as a general rule, every state should have one outgoing for every symbol of the alphabet. What does it mean? For example, if you are here, yeah, you need one outgoing for, yeah, you see A and B. You need one outgoing for A, one outgoing for B. How about here? You need one outgoing for A, one outgoing edge for B. And how about here? Exactly the same thing. One outgoing for A, one outgoing for B. In this way, you won't miss any edges, right? Okay, so now let me give you some notes about this. So this is a very important point. To test your machine, you need to bring all of the strings from sigma star. What does it mean? You are not allowed to use any string outside the sigma star. So if the sigma, for example, is A and B, then what would be the sigma star? Yeah, we already know that. It's with A, B, lambda, A, B, and yeah, you see, all of these strings should be your test cases, either for the L or for L bar. For example, you cannot test the previous machine with, let's say, CAB, because C was not part of the alphabet. You are not allowed to do that, right? So this is a very, very important point here. How can you break a design? So you have two options for breaking a design. Either you should take an example, a counter example, let's say, one string from L that is not accepted. If you can find one string from the L that is not accepted by your machine, the machine is not designed very well. Okay? But the second option is if you find one string from L bar that is not rejected, or let's say one string from the L bar that is accepted. If this is the case, again, your design will break. Now let me ask a $1 million question. Can anyone, anybody, can ever claim that your design or your code is bug free? You need to think about this. After a while, you would say, no, no. So if you just want to test your design, and by testing prove that, hey, my design, by testing, it is bug free, you cannot do that because you need to test all of the strings of sigma star. Some part of the sigma star is L, the rest of them will be L bar. Yeah, you know that. So the union between L and L bar will will be the sigma star. And if you want to just by testing to prove that your design is work, so since the sigma star is infinite, you don't have enough time to do that. So unless you really can mathematically prove, uh, probably by mathematical induction, that your code or your design is working perfectly, in that way, yeah, it's because the mathematical proof is behind that. In other case, no. So all of the designs theoretically can have a bug. Let's take another design example. The set of strings starting with prefix AB over sigma. So all of the strings should start with AB. After the AB, it can be anything. Okay, so the example asks us to write a set builder for that and design a DFA for that. Okay, so let's start with the set builder. Let's see. it should start with AB. Definitely lambda is not part of this. So AB itself, yeah. After the AB, it can be anything, right? It can be A, it can be B, for example, it can be AB, and so forth, right? Okay, so when we say anything after the AB, we learned so far that what does it mean, the anything? We need to use a variable, string variable, to represent that. So our pattern will be AB followed by anything, and then for the explanation here, A and B are constant, but W is a variable. We need to define that W. W belongs to sigma star. So it means that W can be any string after the AB. So this is the set builder. Now let's design that. Okay, so we start from the initial state. All of the string has one A. Okay, so we need to move to here if it is A. And it should be followed by a B. Okay, no problem. We move here. And it can be anything here. So AB itself should be accepted, right? So we make this as an accepting state. And anything after that, when we say W here, which belongs to sigma star, it means that any combination of A and B is accepted. So I put a loop here and I say, hey, after the AB, if it is A or it is B, just loop here, loop, 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 loop here, and stay here. So this is the accepting strings, or the flow of accepting the strings, right? Anything except these guys should be rejected. How can I do that? You just put a trap here. And how we can conduct the rejecting strings to the trap, it's easy. You remember I said we need to have one outgoing for every alphabet symbols, right? So we have one A here, it goes here. We need another B to the trap. So B goes here. How about here? Yeah, B goes here. So we need, if it is A, go here. Do we need anything from here? No, because A or B needed to be looped here. It has already an outgoing for A and outgoing for B, right? So this is our design here. Let's take another example. The set of all strings that contains even number of ones over this alphabet. Okay, first we need a set builder for L and we need a design. Okay, so let's, to understand that what is going on here, even number of ones. So zero number of one is even, right? So this language contains lambda, 1, 4, yeah, 2, 0, and continue, right? I think the pattern is revealing itself. So what is the L here? Yeah, we would say 1 to the 2n such that n greater than or equal to 0. So this 1 is actually the symbol of the alphabet. It's a constant. To n is a number that it needs to be described here. This will be our set builder. Now let's design the DFA. All right. Okay, so the lambda should be accepted. In this case, we make the initial state as an accepting state. And if we have one it should be rejected, right? So we send it here, it should be rejected. But if we have another one, it should be accepted. So how about I return it back to here, right? I think we are done here. So if we have lambda, it will be accepted here. If we have 1, 1, it goes 1, 1, will accept here. If we have 4, 1, 1, 2, 3, 4, and you agree that even number of ones return back to here and it will be accepted. Based on this knowledge that we got so far, I put some exercises for you guys. So here we have even unary number. What is the difference between this and the previous slide? So unary number, remember that it does not have lambda. It starts from the 2, 1, 1, I mean 1, 1, and 4, 1, and so forth. So just remove this and redesign whatever we did in the previous slide. We have a bunch of other exercises here. L equal to sigma star. So it means that your language should accept everything. I asked you to write a set builder to represent the language and design a DFA for all of these languages. Okay. And we have another set of the examples here that are definitely harder than the previous slides. So the set of strings containing exactly 1A, we already know how to write the set builder. Now we will need a DFA for that and at least 1A ending with suffix AB, right? Okay, so I do recommend you guys go over all of these exercises and practice and practice and practice. So I'm gonna stop here. See you guys in the next lecture.